We'll get started. So, chapter 23, part 2 homework is due today. Chapter 24 homework is due on the 1st. The exam for chapters 22 through 24 will be on the 1st. And we'll have a review on Monday next week. So next week we have the exam, Monday will be review, Wednesday will be the test. So continuing on, the electromagnetic spectrum, all electromagnetic waves have the same speed in a vacuum. So the relationship between wavelength and frequency is simple. Speed of light equals frequency times wavelength. And the full range of frequencies of electromagnetic waves is called the electromagnetic spectrum. And it varies from long wavelength things like radio and TV, then microwave, infrared, visible light, ultraviolet light, X-rays, and then short wavelength stuff like gamma rays. So radio waves are the lowest frequency electromagnetic waves that we find useful. Radio and television broadcasts are 10 to the 6 hertz, 10 to the 9 hertz. Microwaves get used for cooking and for telecommunications. The microwave frequencies are 10 to the 9 hertz, 10 to the 12 hertz, with wavelengths from 0.3 millimeters to about 30 centimeters. Infrared waves are felt as heat by humans. Remote controls operate using infrared radiation, and their frequencies are from 10 to the 12 hertz to 4.3 times 10 to the 14 hertz, which is the lower end of human ability to see light for red. Visible light is fairly narrow, from 4.3 times 10 to the 14 hertz red to 7.5 times 10 to the 14 hertz violet. That's 700 to 400 nanometers in wavelength. Ultraviolet light starts with frequencies just above those visible light at 7.5 times 10 to the 14 hertz and goes up to about 10 to the 17 hertz. So long wavelength ultraviolet, not that big of a deal. Short wavelength ultraviolet can cause tanning, burning, and skin cancer. Some insects can see in the ultraviolet, and some flowers have special markings that are only visible under ultraviolet light. X-rays are higher frequency still, from 10 to 17 hertz to the 20 hertz. They're used for medical imaging. And then gamma rays have the highest frequencies, above 10 to the 20 hertz. And these are extremely energetic and are produced by nuclear reactions. They're destructive to living cells and can be therefore used to destroy cancer cells and to sterilize food. When it comes to terminology, the line between X-rays and gamma rays gets fuzzy because there's some historical naming conventions going on where to some people, if it comes from radioactive decay, it's a gamma ray, and if it comes from not radioactive decay, it's an X-ray. To other people, they just draw the line at 10 to the 20 hertz. It's more or less arbitrary. The terminology thing. These divisions are arbitrary. So, we can talk about energy and momentum of electromagnetic waves. So, we looked at the energy density of an electric field. It's 1/2 E naught times the electric field squared. And for a magnetic field, well, that's 1/2 mu naught B squared. Therefore, we can add together the energy density of the electric field and the energy density of the magnetic field to find the energy density of an electromagnetic wave. And it can be shown that the energy densities in the electric and magnetic fields turn out to be equal. 1/2 epsilon naught ERMS squared plus 1/2 mu naught BRMS squared equals epsilon naught times ERMS squared, or 1/mu naught BRMS squared. Therefore, 1/2 epsilon naught E squared equals 1/2 mu naught B squared. So the electric field is 1/2 square root of epsilon naught mu naught from the magnetic field, or the speed of light times the magnetic field. Turns out they're nicely related. Now, the energy that a wave delivers to a unit area in a unit time is called the intensity. So that's going to be watts per unit area. Intensity is energy over area times time. So that's energy density times area times speed of light times delta t over area times delta t. Delta t cancels, area cancels. We get energy density times the speed of light. So if we substitute for the energy density, I equals U times C, which is 1/2 C epsilon naught E squared, 1/2 mu naught C B squared, or C times epsilon naught E squared, or C over mu naught B squared. And it will also carry a momentum of energy over C. Therefore, it ends up exerting a pressure, which is the average intensity over the speed of light. And so radiation pressure can be used to push things. And here, for example, radiation pressure is responsible for the curvature of this comet's dust tail. Actually, because what's going on is that this tail here is being kicked off by the solar wind. So the sun emits charged particles, they're whacking into stuff, knocking the gas tail off back. The dust tail is not pushed as hard because it's primarily pushed by light. And so it trails behind. And that's why it's curved. Because the comet is going this way. Because the comet's tail points away from the sun. So the comet is going like this way. So at a given instant of time, the electric field in a beam of sunlight has a magnitude of 429 newtons per coulomb. So let's get some of these formulas down. We know that average energy density ends up being epsilon naught RMS, which equals 1 over mu naught squared. So electric field equals C times magnetic field. And then intensity ends up equaling delta U over area times delta T, which ends up equaling energy density times the speed of light. And momentum is energy transmitted over C. So pressure is average intensity over C. And the units for intensity is watts per square meter, power per square meter. So at a given instant of time, the electric field in a beam of sunlight has a magnitude of 429 newtons per coulomb. What is the magnitude of the magnetic field at this instant? I'll let you think about that for a minute or so. So electric field equals speed of light times magnetic field. So magnetic field equals electric field divided by speed of light. 429 newtons per coulomb divided by 3 times 10 to the 8 meters per second gives you 1.43 times 10 to the minus 6 Tesla. So it's small. Ugh. So here we have a garage illuminated by a single incandescent light bulb that is dangling from a wire. If the bulb radiates light uniformly in all directions and consumes an average electrical power of 50 watts, what is the average intensity of the light? And the root mean square values of E and B at a distance of 1 meter from the bulb. Assume that 5% of the electrical power consumed by the bulb is converted to light. Okay, so I'll go through how we can do this process. So intensity is energy per time over area. So it's power over area. The power that is light is 5% of the total power, so 0.05 times 50 watts, so it's 2.5 watts is converted to light. The area is 4 pi r squared, or 4 pi times 1 meter squared, or 4 pi square meters. So 2.5 watts divided by 4 pi gives you an intensity of 1.99 watts per square meter. Intensity is equal to the speed of light times epsilon naught times the electric field squared. The electric field squared is intensity divided by the speed of light times epsilon naught. So the electric field is the square root of that. So the square root of 0.199 watts per square meter over 3 times 10 to the 8 times 8.85 times 10 to the minus 12 gives you 8.66 newtons per coulomb. And then to get the magnetic field, we divide that by the speed of light, and we get 2.88 times 10 to the minus 8 Tesla. Any questions about this? Okay, I will just continue. So when an electromagnetic wave carrying an energy U is absorbed by an object, the momentum the object receives is pi, u over c. If instead the object reflects the wave, is the momentum the object receives greater than, less than, or the same as when it absorbs the wave? So you can either have the light hit it and get absorbed, which will transfer PI, momentum of the light, or it can hit it and bounce off. Which do you think transfers more momentum? Yep. Because when it hits it and absorbs, it just gets PI. But when it bounces off, the light has momentum in the opposite direction after it bounces off. And so it has to get more than PI transferred. The more momentum is received, the more active wave has momentum in the opposite direction. So if you want to, push something with light, you reflect the light off of it, which is why if you're designing a solar sail, you make it out of shiny material. So NASA's Kepler Space Telescope is is orbiting observatory that searches for Earth-like planets orbiting distant stars. When two of the reaction wheels used to stabilize the telescope failed, the mission almost came to an end. Fortunately, a plan emerged to use radiation pressure from sunlight shining on Kepler's solar panels to help point the telescope. If the average intensity of sunlight in Kepler's orbit is 1,350 watts per square meter, what is the average force it exerts on the solar panels? Assume the panels have an area of 10.2 meters squared, and they absorb all the light that falls on them. Because they're solar panels that are designed to absorb light. Actually, something similar is currently happening with the Hubble Space Telescope, because its reaction wheels have been steadily failing. So I believe they're using radiation pressure. I'm not 100% sure on that. So pressure is, momentum is U over C, which reads momentum is intensity times area times time over C. Force is dp dt. So force is going to be momentum over T. So the T cancels and you get force is intensity times area over C. You could also do that pressure is average intensity over C, and then you multiply that by area. So that's the other way you could solve this. You could say that pressure here is average intensity over C, and then it's just intensity, pressure times area is force. So intensity times area over C is the force. So that's 1,350 watts per square meter times 10.2 square meters divided by 3 times 10 to the 8th meters per second, which gives you 4.59 times 10 to the minus 5 newtons. Not a lot of force, but it's a consistent force that you can work against. So, the polarization of an electromagnetic wave refers to the direction of its electric field. Most light sources generate unpolarized light. The directions are basically randomized. But certain situations will have polarized light. So you can have light that is polarized, say up and down, or at a 60-degree angle, or to the y direction, things like that. So polarized light has all its electric fields in the same direction, while unpolarized light has its electric field in random directions. Now, a beam of unpolarized light can be polarized by passing it through a polarizer, which is basically a thing with a bunch of slots that only allows a particular component of the electric field to pass through. This is a mechanical analog with a slot. This is an actual polarizing film. So this polarizing film is only allowing light to go, the electric field to go up and down, I think. If I put another one in front of it, not much happens. But if I cross them, it blocks the light. And if I have one at 45, and then this would be blocking it, you can see some gets through if I polarize it 45 degrees in between. You can see how some of it is completely blocked, but where there's this one at an angle, some of it gets through. Hopefully that's visible on the recording, but if not, I have a video. So a polarizer will transmit the component of light in the polarization direction. So vertically polarized light of intensity I naught, polarizer, if a polarizer is at some angle theta to it, it will transmit the component of that, which will have intensity of cosine theta squared. Because intensity is proportional to the amplitude squared. That's a property of waves. Since the intensity of light is proportional to the square of the field, the intensity of the transmitted gain is given by the law of Malus. Which is that intensity is initial intensity times cosine of theta squared. And the light exiting from a polarizer is polarized in the direction of that polarizer. So if an unpolarized beam is passed through a light polarizer, so polarized, the intensity will just be half the initial intensity. Because it's randomly distributed, it lets through the vertical, it kills the horizontal. So a polarizer and an analyzer can be combined, where if you have unpolarized light, it goes through a polarizer and then through another polarizer at some angle. And the final intensity will be 1/2 the initial intensity times the cosine of that angle squared. And that is how your LCD screen works. Except there's a liquid crystal in the middle which rotates the polarization as it passes through, and the amount that it rotates can be adjusted electrically. And that's how they can make lighter and darker pixels. So here's a video showing an LCD screen. Linear polarization stacking gate go. Okay, so that's not polarized light behind. Now, that light source is not there. But my phone, for example, is polarized. So if I hold light here, and that's because the way an LCD screen works is that there's a polarizing layer, there's a layer of liquid crystal, and the liquid crystal, depending on the voltage applied to it, twists the polarization. And that's how you can turn on and off certain pixels. So the light coming out of your phone is always polarized if you have an LCD screen. And here's another demo of polarization and polarizers.
Here's a single sheet of polarizer, a kind of filter that lets through only electric field vibrations that are in a certain direction called the transmission axis. I've marked the transmission axis on the polarizer with that double-headed arrow. Vibrations perpendicular to that are blocked, absorbed by the material. This polarizer is in front of a light table, and the light waves coming at you are wiggling up and down, left and right, and every diagonal direction. Those diagonal vibrations, however, can be thought of as simultaneous vertical and horizontal vibrations. So we can think of the light as having only vertical and horizontal components of vibration. And this polarizer, as it's oriented now, is letting through only the vertical vibrations. If I turn it, however, then the light getting through is now vibrating horizontally. Here's a second polarizer. With the two transmission axes parallel to each other, there's not much difference where they overlap. The first filter, closer to the light source, blocks almost all of the horizontal vibrations and lets through the vertical vibrations. The second one, closer to you, lets almost all the vertical vibration through. It would block horizontal vibrations, but there are no horizontal vibrations hitting it because they were blocked by the first polarizer. Now, if I rotate the foreground polarizer, what will happen? Let's see. The first polarizer blocks the horizontal vibrations. The second blocks the vertical vibrations, so essentially no light gets through. I say essentially because the filters are not 100% perfect. Now I'm going to put a horizontal polarizer on a stand here in the foreground, so I have a hand free to introduce a third polarizer, a small one, in between the first two. Notice that some light gets through when the small polarizer is diagonal, but no light gets through when the small polarizer is either vertical or horizontal. Can you explain why?
Okay. So LCDs use liquid crystals, whose direction of polarization can be rotated depending on the voltage across them. So basically what you do is you have a polarizer, the liquid crystal cell, and then the analyzer. And the liquid crystal rotates the polarization of the light coming into it. And the amount that it rotates can be adjusted by the voltage going across it. It turns out modern ones The first ones did like 0 to 90 degrees, but modern ones actually do something like 180 to 270. Because it turns out that gives you better and faster response times. Like, it just makes a better screen. It takes less voltage, less power. But here's an example. So here, transmitted light is a bright background. It's rotated 90 degrees, so it comes out the analyzer. It's not rotated, so it's dark. Now, unpolarized light can be partially or completely polarized by scattering from atoms or molecules, which act as small antenna. And if the light is already polarized, its transmission will depend on its polarization, which means that light reflecting off of a surface can end up polarized and often ends up polarized parallel to that surface. So what this means is that sunlight will be polarized depending on the angle our sight makes with the direction of the sun. The transmitted light is unpolarized and mostly red, while the scattered light is polarized and mostly blue. And the light reflecting off of things, when light reflects off a smooth surface, that can cause things often to be horizontally polarized. And that's why polarized sunglasses are vertically polarized, because the glare from reflection off of surfaces is usually horizontally polarized. So if you wear polarized sunglasses, kills the glare. So if you have vertically polarized light with an intensity of 428 watts per square meter, it passes through a polarizer oriented at an angle theta to the vertical. What is the transmitted intensity of the light? For theta equals 15 degrees, 45 degrees, and 90 degrees. So this, you'll be using this. Intensity is initial intensity times the cosine of the angle squared, because you're going in with already polarized light. So intensity is initial intensity times the cosine of the angle squared. So for 15 degrees, it's 428 watts per square meter times the cosine of 15 degrees squared, which will be 399 watts, 399.3 watts per square meter. For 45 degrees, it's 428 watts per square meter times the cosine of 45 degrees squared. This works out to half the intensity, 214 watts per square meter, because the cosine of 45 degrees is 1 over the square root of 2. So when we square it, we get a half. And at 90 degrees, no light makes the intensity is 0. So here we have a polarization. We have an incident unpolarized beam. We have one polarizer here, and then we have another polarizer at an angle of theta. And the transmitted beam is 0.2 of the initial source beam. So if the final intensity is 0.2 of the initial source beam, what angle is theta between the transmission axes of the analyzer and the polarizer? So remember, the first polarizer is going to cut the intensity in half. And then the second polarizer will take that input and multiply it by the cosine of the angle squared. So the final intensity coming out is 1/2 the initial intensity times the cosine of the angle squared. Because again, the first polarizer is cutting it in half. And then the second polarizer is taking that 1/2 intensity squared and multiplying by the cosine of the angle squared. So that final intensity is 0.2 times I naught. The I naughts cancel. And so we get 0.2 equals 1/2 cosine theta squared. So 0.4 equals cosine squared theta. So the square root of 0.4 equals cosine theta. So if you take the inverse cosine of the square root of 0.4, you get 50.8 degrees. If this had come out at 0.25, it'd be 45 degrees. So here, we want to do the transmitted intensity for the following cases. We have a vertically polarized beam of intensity 0, passes through a polarizer with its transmission axis at 60 degrees to the vertical. That's A. And B, a vertically polarized beam of intensity I0 passes through two polarizers. The first with its transmission axis at 30 degrees to the vertical, and the second with the transmission axis rotated an additional 30 degrees to the vertical. In both cases, the final beam is polarized at 60 degrees to the vertical. And you're starting with a vertically polarized beam. We're always going to be using this formula. In the first case, you have a vertically polarized beam. It hits a single polarizer that's 60 degrees from the vertical. The second case, you have a vertically polarized beam. It hits one at 30 degrees from the vertical, and then a second one at 60. So you're basically adding an extra polarizer in between. So, in general, the intensity that comes out is going to be the initial intensity times cosine squared theta. In part A, well, we're only going to do that once. So final intensity is initial intensity times cosine squared theta of 60 degrees. Which is 0.25 initial intensity. Well, here, after the first polarizer, it'll be initial intensity times cosine squared 30 degrees. Then after the second polarizer, it'll be what you got from the initial one times cosine squared 30 degrees. So I2 is going to be I naught times cosine squared 30 degrees times cosine squared 30 degrees, or cosine of 30 degrees to the fourth power, which comes out to 0.5625 times the initial intensity. Because cosine squared 30 degrees is 0.75, and then 0.75 times 0.75 is 0.5625. So by adding a polarizer 30 degrees to the vertical in between, we more than double the output intensity. So here we have a set of three polarizers. Polarizer 1 has a vertical transmission axis. Polarizer 3 has a horizontal transmission axis. The polarizer 1 and 3 are a pair of cross polarizers, so when a beam of unpolarized light shines on polarizer 1 from the left, no light emerges from polarizer 3. If we put polarizer 2 at 45 degrees to the vertical in between polarizers 1 and 3, is the transmission of light through the three polarizers zero or non-zero, and which is the best explanation? No light can pass through the cross polarizers 1 and 3, regardless of what other polarizers are placed between them. Or polarizer 2 changes the polarization direction by 45 degrees, and light cannot pass through polarizer 3, which is the correct description there. What? No, it's 2. I literally did this a little while ago. Oh, the second one. Sorry. I heard 1. Yes, the second one. So that's the end of chapter 25. Electromagnetic waves are traveling waves of oscillating electric and magnetic fields. Electromagnetic fields in an electromagnetic wave are perpendicular to each other and the direction of propagation and are in phase. And a right-hand rule gives the direction of the fields of propagation. Any accelerated charge will emit electromagnetic waves. Electromagnetic waves can travel through a vacuum. Their speed in the vacuum is always 3 × 10⁸ meters per second. There's the formula for the Doppler effect. The change frequency is the frequency of 1 plus or minus the speed over c. Electromagnetic waves can have any frequency. The entire range of frequencies is called the electromagnetic spectrum. The relationship of frequency and wavelength is the frequency times wavelength equals the speed of light. This is the formula for the energy density of an electromagnetic wave. The electric field ends up being the speed of light, c times the magnetic field. The intensity of an electromagnetic wave is energy density times c, which is 1/2 c naught times electric field squared. C times E naught times electric field squared. Momentum of electromagnetic wave is the energy divided by the speed of light. Radiation pressure ends up being average intensity over the speed of light. The polarization of a beam of light is the direction of its electric field. A polarizer transmits only light whose electric field has a component along the polarizer's axis. An initially polarized beam of light encountering a polarizer at angle theta has a transmitted intensity I naught times cosine theta squared. If we start with initially a polarized beam of light hitting the polarizer at half the initial intensity, light scattered from the atmosphere is polarized when viewed at right angles to the sun. When light reflects from a horizontal surface, it's partially polarized in the horizontal direction. And then we'll finish off today with some bits of chapter 14 that we hadn't covered already. So superposition and interference. If waves of small amplitude traveling through the same medium combine or superimpose, they just add together. This happens with light. If two pulses combine to give a larger pulse, this is called constructive interference. If they combine to give a smaller pulse, this is called destructive interference. And two-dimensional waves exhibit interference as well. Here's an example of an interference pattern. And here we have waves from two sources combining, and in some places you'll have constructive interference, in some places you'll have destructive. I can show you an example of waves from many sources combining and creating constructive and destructive interference. This is where waves from many sources combine and do constructive and destructive interference. We get a nice pattern. But this has lots of little lines on it, each of which acts as an individual source. This is diffraction rate. So points where the distance to the two sources differs by an equal number of wavelengths will interfere constructively. That was where we got the dots. In between, the interference will be destructive. And because that has many sources combining, it accentuates it. It's not a gradual variation. You get very bright dots and nothing in between. Beats are an interference pattern in time rather than in space. If two sounds are very close in frequency, the sum has a periodic time dependence that is at the beat frequency, which is the difference in their frequencies. That's not really important with light very often, but that is a thing that you hear more often with sound. So a wave is a propagating disturbance. This is some summary stuff for chapter 14. Yeah, that's all I wanted to cover from chapter 14. Any questions? And if not, we'll just do the lab. So I'm gonna stop sharing and